There is tremendous growth in the development of novel metal organic frameworks for a wide variety of separation applications. The efficacy of a developed MOF for a specified separation task is usually demonstrated using a three-pronged approach. This consists of measurements of unitary isotherms, the use of the Ideal Adsorbed Solution Theory for determination of mixture adsorption equilibrium and calculation of adsorption selectivities and uptakes in mixture adsorption. The separation efficacy is further established and validated using experimental breakthrough data carried out in small scale equipment, typically with internal diameters of around 5 millimeters with pack lengths of about 10 centimeters. For background on the theory for the evaluation of MOFs and analysis and simulation of breakthroughs, I refer you to my papers listed here. Watch also many YouTube presentations that address each of these three aspects in considerable detail. In my YouTube presentations, I've also highlighted and underscored a variety of scenarios under which the Ideal Adsorbed Solution Theory fails. It is therefore quite remarkable to note that measurements of mixture adsorption equilibrium are very scarce in the published literature, and it is much easier for experimentalists to perform breakthrough experiments rather than to conduct experiments to determine mixture adsorption equilibrium. It is this topic I wish to address in this presentation. There is tremendous interest in the use of Calgary Framework 20 for CO2 capture from humid flue gases. Nguyen, Shimizu, and Rajendran published a set of experimental data for feed mixtures consisting of CO2 containing water vapor to varying degrees of relative humidities. The breakthrough experiments were analyzed to determine the component loadings as a function of the percentage relative humidities. The CO2 loadings are indicated by the red circles, and the blue triangles are the loadings of water. It is noteworthy that the breakthrough experiments are not conducted under precise isothermal conditions, and in the early stages of the transient breakthroughs, we have temperature overshoots. Another point to note is that for the two experimental data points at the highest values of percentage relative humidities, the component loadings for water exceed even the unitary loadings corresponding to that percentage relative humidity. such increase in the water loadings over and above the values predicted from urinary isotherms are difficult, if not impossible, to capture using standard procedures for modeling mixture adsorption equilibrium. The predictions of the IAST are in very poor agreement with the experimentally determined loadings for CO2 and for water. At low values of relative humidity, the CO2 loadings are higher than those anticipated by the IAST, and for high values of relative humidity, the CO2 loadings are significantly lower than the estimates of the IAST. I've explained these characteristics in earlier video presentations on my YouTube channel that are titled Thermodynamic Non-Idealities in CO2 Capture with CALF-20. In part 6 of this series, I demonstrate that these 2 points are rogue points and do not conform to the thermodynamic consistency requirements imposed by the application of the Gibbs-Duhem equation and the requirements of the excess Gibbs free energy models for mixture adsorption equilibrium. I asked the question, what would happen if we were to measure CO2 water equilibrium under conditions similar to those in the breakthrough experiments? Would we also observe deviations from the ideal adsorbed solution theory as noticed here? Researchers from Matrix Sensors Incorporated in San Diego, California, have developed a novel technique that measures mixture adsorption equilibrium using thin films of sorbents deposited onto sensitive micro-electromechanical system transducers, MEMS. This technique is fast, requires very little material, and enables real-time monitoring of binary gas mixture adsorption in MOFs and other nanoporous materials. This development is reported in this paper titled Thin Film Approach to Rapid Quantitative Measurements of Mixed Gas Adsorption Equilibrium in Nanoporous Materials. And this paper is co-authored by researchers from Matrix Sensors and also researchers from the universities of Amsterdam and Calgary. The thin film approach was used to measure CO2 water mixture adsorption equilibrium in pristine CALF-20 materials. The experimental data on the component loadings for CO2 indicated by red circles and water, blue triangles, for adsorption of CO2 water mixtures at a temperature of 298 Kelvin are shown in this graph here as a function of percentage relative humidity. The total pressure of CO2 and water is 15 kilopascals. We note that the experimental data also shows strong deviations from the estimates of the ideal adsorbed solution theory. The continuous solid lines are the real adsorbed solution theory fits of the experimental data. Another way to demonstrate the deviations of the experimental data from the IAST is to plot the mole fraction of CO2 in the adsorbed phase on the y-axis as a function of percentage relative humidity. For values of percentage relative humidity is lower than about 30%, the adsorbed phase is richer in CO2, i.e. poorer in water than anticipated by the IAST. On the other hand, for relative humidities in excess of 30%, the adsorbed phase is significantly poorer in CO2, i.e. richer in water than anticipated by the IAST. The RAST modeling using the Margulis model for activity coefficients is shown here by the continuous solid lines. These are the activity coefficients for CO2 indicated in red and for water in blue. This is the plot of the excess Gibbs free energy as a function of mole fraction of CO2 in the adsorbed phase. The experimental data, as reported by matrix sensors, is thermodynamically consistent. Further details are provided in the preprint I had referred to earlier. In my paper co-authored with Jasper van Baarten, published in Separation and Purification Technology with the digital object identifier as specified here, we present configurational bias Monte Carlo simulations for a set of conditions identical to those used in the matrix sensors incorporated experiments shown in the foregoing slide. The CBMC data for mixture adsorption equilibrium for CO2 indicated by red circles, water indicated by blue triangles are shown here as a function of percentage relative humidity. As in the experiments of matrix sensors, we note that at percentage relative humidities lower than about 25%, the adsorbed phase is significantly richer in CO2 than anticipated by the ideal adsorbed solution theory. On the other hand, for percentage relative humidities higher than 25%, the adsorbed phase is significantly poorer in CO2, i.e. richer in water than anticipated by the IAST. The RAST, or Real Adsorbed Solution Theory, calculations are shown by the continuous solid lines, and these are the activity coefficients in the adsorbed phase. The message to emerge from this is that the CBMC simulations are in agreement with the trends observed experimentally and the reasons for the deviations of the experimental data and the CBMC simulation data from the predictions of the IAST are as described in my paper in separation purification technology. I've also prepared a video on this topic. Watch thermodynamic non-idealities in CO2 capture with CALF-20, parts 1 and 3 on my YouTube channel. The important message that emerges here is that with the development of the thin film approach developed by Matrix Sensors Incorporated, we can measure mixture adsorption equilibrium rather than having to rely only on mixture breakthroughs experimental data that are subject to some thermodynamic inconsistencies due to non-conformation with the requirements of precise isothermal conditions.